the idea of Runge-Kutta, so it's essentially generalization. It's like, you remember we studied trapezoid, rectangular, left rectangular rule, trapezoid rule for integration, then midpoint, Simpson, right? So all of them we introduced ad hoc. So in other words, we just said, okay, let us try to use interpolation using, let's say, polynomial of degree 2, and so on. So, and then after that, we said that, okay, in general, this is called Newton-Cotes methods, closed methods, open methods, and so on. Here we have more or less the same idea. So essentially, what we can do, so we can, so what's going on? Looks like my iPad updated without permission and started to give me troubles after that, because every software just getting worse, not better. Okay. So idea is that, for example, midpoint method. So so if we consider the following initial value problem. So you remember, midpoint method is that when we integrate left-hand side from t to t plus tau by dt, and the right-hand side from t to t plus tau by dt. And what we are getting yt plus tau minus yt. And in the right-hand side, we use approximation of this integral using midpoint rule, so which is f. This. But of course, the problem is that here we, instead of that, we need to use some approximation because we don't know our value of our solution at the point at the point t plus tau divided by 2. So we use the following. We use just approximation using Euler's method. Just this. So this idea that instead, so we can apply essentially different integrating rules to the right-hand side here, and instead of corresponding points, you remember, for example, Simpson rule requires so when we integrating from t to t plus tau, for a Simpson rule, we need also these, and then we can apply the Simpson rule, midpoint, right? We need midpoint. So essentially, idea is that you can use different linear combinations of your function evaluations of your functions in some middle points and so on. So, and essentially, this idea that you're just replacing this integral in the right-hand side with some formula for numerical approximation of this integral, higher and higher order. So, and then you can find the right linear combination in here in order to get the order of the methods which you like. For example, let me give it to you. So if you want to use order 3, Runge-Kutta method. Yeah, and as I said, so Euler is Runge-Kutta method of order 1. Trapezoid is, which means approved Euler, right? Is also Runge-Kutta method of order 2. It's essentially the same idea that this is generalization, like Newton-Cotes rule, right? So generalization of all the previous rules which we had. So here it's more or less the same. For example, so let us consider first, okay, order 2, one of the order 2 methods. No, let us do immediately order 3. Yeah. So idea is the following, that t plus tau will be approximated by y at t plus h or tau 6, and here is S1 plus 4S3 plus S2. So S1 is nothing else but the right-hand side. S2 is nothing else but evaluation of the solution on the end of the interval. And S3 is evaluation of the solution in the middle of the interval, just using information from the previous steps. So have a look. First, you compute this, it's just the right-hand side. And then, so essentially, this is what you do. This is your, yeah, I have this picture already. So it's essentially like an application of the Simpson rule. So here you can see that this is nothing else but Newton-Cotes rule of the, I mean, it's just Simpson, right? So with the weights, corresponding weights and values of your function. So here you use just the value of your function. So you know this, it's this one, right? Now, in order to apply Simpson, you need to know value of your function on the last point, I mean, the end point of the interval, right? Of this small step. Then what you do, so have a look, what is that? Could you tell me what is this thing? So it's nothing else but exactly so could you tell me what method I used here to evaluate value of my function on the end point of the of my small interval from t to t plus tau?
That's just Newton's method.
Not, you mean Euler, right?
Euler, sorry, yeah.
Yeah, I understand. This
Nice.
is the end of the semester,
Yeah.
the last week of classes. So probably you're not sleeping that much. Okay, so you see, we are using Euler's method in order to evaluate. So here, f at t plus tau, y at t plus tau, right? So we don't know this exactly, right? So this is why we use this. Okay, so we found the value here, but now for Simpson method, we need also, sorry, to evaluate my function in the midpoint, right, for the Simpson. So how I do this? You see, I decided to use the information, previous information. So I'm just taking the average of them. So this is again like a, you see, I could do here the following. F t. So essentially what it means, it's f at t, y at t, tau, right? So again, Euler's step. But so what is this f? Remember, f is nothing else but the slope of the derivative, right? So what I'm doing, so instead of using just Euler, using information from here, f of t, t y t, like that. So I know slope here. I know slope here already because I essentially evaluated it, right? Using Euler's, exactly this. So here I'm taking the average slope. So instead of that, I'm using this thing, which is average slope from the information which I have. And then I'm making I'm making the half step in order to get to this point. This point. Is it clear what is going on? So essentially you compute S1, then you use it here. Then also you use S1 as value of your function here. And then you use both S1 and S2 in this computation and compute the slope or your function in the middle. And then you have 3 points, this, and that. And you can use Simpson rule, which is here, in order to integrate your function on this interval of time from t to t plus tau. Is it clear or not what is going on? Hello, anybody? If it's not clear, you please ask questions.
I think it's mostly clear. So this is basically just kind of using Simpson's method.
Yes,
right.
Yes,
okay.
I'm just explaining that. You see, for Simpson method, you need to evaluate values of your function on the. Okay, let me use different color. Okay, for Simpson, you need to know your function here, here, and here, right? But if you want to do the integration, right? So originally, you know your function only here, right? Here you can evaluate your function like that, function f, which you are applying. But in order to integrate using Simpson, right? So here, to evaluate this integral, you need to know also your function in this point and in this point, right? It's exactly the same as what we have done for the midpoint rule or for the trapezoid rule and so on, right? Yeah, by the way, here divided by 2. Okay, so then what I'm doing, I'm using Euler to get value of my function in this point. But the value of my function in this point includes this y at t plus tau. But this is exactly what I'm trying to find, right? So I'm trying to find my y at this point, at the end of the interval. So I don't have it. So this is why I'm using the Euler's rule to make a step there. Just some approximation. Okay, I found it. Then now I need to find value of my function in the middle point, right? In order to use Simpson. So how to do this? So essentially, this is the value of my function in the middle point. So here everything is easy. So you just add to t step divided by 2, half step. But here you need to use again Euler. So because this is nothing else, this part is nothing else but oops, not y. This is nothing else but f t plus tau divided by 2 y at t plus tau divided by 2, right? But once again, I don't know this function, so I'm trying to evaluate it using something similar to Euler. Just for the slope, I use not just information on this side of the interval, but information from both sides of the interval. I'm taking the average slope. Here it is. Is it clear or not?
Yeah, I think that makes sense to me.
Okay, anybody else has questions or comments? Okay. Either everybody is sleeping or nobody cares really. Okay. Now, it's very similar to remember order 2 Runge-Kutta method. So which we used, which was essentially nothing else but trapezoid. So for trapezoid, you also need it in order to evaluate your integral, right? You need to know, so if this is t plus tau, right? So here you need to know f. So this information you have for the right hand side, but here you need to know f t plus tau y t. Wait a little bit. T plus tau. But this is exactly what you're trying to estimate, right? So this is why instead of that, you use approximation. So essentially, you're saying that you're using, first you're finding S1, which is f t y. So it's value of your function in this point. And now you need to find value of your function in this point. So S2 is f t plus tau y t plus S1 tau, because this is nothing else but that. So this is nothing else but Euler step, right? And after that, you can write that using trapezoid method. So you use essentially okay, S1, S2. Or you can say that you use average slope. Down. That's it. So this is nothing else but trapezoid rule, right or not?
Right.
Yeah. So idea is that you can use, and this is nothing else but Newton-Kotezo order 2, right? Closed rule. So idea is that you are finding these slopes, this function f, in different points using this combination of Euler step and information from what you already know, right? Okay, now, so once again, the only thing which I want to tell you that order 2 Runge-Kutta methods are, of course, they are not unique because, for example, the midpoint method, right? So order 2 Runge-Kutta midpoint. So this is nothing else but improved Euler, right? So as we studied, but this is another Runge-Kutta method. So using midpoint. So as you understand, this will be just yt plus, and here once again the slope, the initial slope which I have is this, and then I need to evaluate S2, the slope in the midpoint here, and multiply it by tau. But slope in the midpoint is nothing else but ft plus tau divided by 2, yt plus S1 tau divided by 2. S1 is nothing else but this. So once again, you're using Euler step. So it's exactly the midpoint method which we used here. So the only difference is that here you use Newton-Kotezo of the second order, but open rule, right? So midpoint. Okay. Now, idea is that you using successive evaluation of slopes, you can find corresponding values of your function in the necessary points, and so you don't need to remember these things, so they are all available in so I of course ask you to know how to derive the simplest ones, like okay, how to understand how we derive Euler. So essentially integrate left hand side and the right hand side of our ordinary differential equation, and this is what we are getting, this and some approximation of the integral in the right hand side, right? So that's it. So you need to know how to derive at least Euler, improved Euler, and maybe midpoint. That's it. So I'm not asking you for anything higher. For everything higher, so you will use just either Abramovitz-Tikhon or other reference books, or for example your textbook. So where all these coefficients are given, and as I said, so for example here for order 2 Runge-Kutta, so you see you can use this approach, you can use this approach. So Runge-Kutta methods are not unique, so you can use different location of points to get the required order of the method. Okay, so but by the way, so could you tell me how we evaluate complexity of the integration method? I told about it on the last lecture.
I think it was how many function evaluations?
Yes, how many right-hand side function evaluations we need to do. So here, how many evaluations for this order 2 method I need to do?
2.
2, right? Because you see, I'm doing it once, right? And here I'm using the previous information and do 2 function evaluations. What about here in the midpoint method?
Also 2.
Also 2, right? What about a third order method, Runge-Kutta third order method? 1, 2, 3, right? So we are using 3 function evaluations, right? For Runge-Kutta 4 method, so idea is the same. So, okay. So y t plus tau equals to y t Runge-Kutta 4 plus, and here is correspondingly, so we use S1 plus 2 S3 plus 2 sorry, S2 S3 plus S4 divided by 6 divided by H. So if you will have a look, it's also one of the Newton-Cotes rules. Okay. Closed rule, because you see the value of your function, the slope from the end point comes into play. So it's something like that. So this is my 1, this is my 2, 3, 4. And so you use one of the rules. Okay. S1. It's just, once again, evaluation of my function. At this point, next, S2. So here, it's a little bit different, as you will see, the Runge-Kutta 4. So really, sorry, I will redraw it. Yeah, really, you use 2 evaluations at the midpoint. It's a little bit more advanced. So then what we use before t plus tau divided by 2, y(t) plus S1 tau divided by 2. So you see it's standard step, exactly the same as what we use, for example, for midpoint rule, right? So let's say this is our S2. Then you can do S3 using already this. So t plus tau divided by 2 y(t) plus, and so if here you used S1, then here you use S2 already this, and making this half step. And this is your S3, the value of your function again, and the midpoint just evaluated using different slope. And then for S4, you use, so here is S4 in this point, t plus tau yt plus s3 tau. So you essentially approximate better and better your function in the midpoint, and then use this better approximation here. Okay, really it's a little bit more complex, but okay, this is, you can see it like that. So okay, let me write it. So if you would use Simpson, this is how it would look like, right? Right? So this is Simpson. Is it clear or not? So value of the function on the left, value this one, value of the function at the midpoint, value of your function on the right end of the interval. Is it clear or not?
Yeah, that's clear.
Okay, and now for SM, you essentially use nothing else but S2 plus S3. So two evaluations of the function in the middle point divided by 2. And this is how you get this Runge-Kutta method. Is it clear or not? Any questions?
Yeah, I think it's clear. It's basically with S2 and S3, you're just taking kind of like an average to get a better guess at what that midpoint is, right?
Yeah, so it's like Runge-Kutta of order 3, but you make extra step to evaluate this midpoint value a little bit better. So once again, all these things, all these coefficients here, you don't need to remember them. You just open any book or okay, you most probably will Google it, so it's available everywhere. So people have done these derivations and obtained these results. So next, okay, this is all good, but there is just some small problem. So for example, y of t, and let's say that we are t plus tau, t plus 2 tau, and so on. And here is our final moment of time where we need to get our solution. And let us suppose that our function looks like that. So then if you use a homogeneous step, or step is the same from the left side to here. So it's obvious. So you just remember, for example, you are using Euler, right? Although never do this, but in real applications, use at least improved Euler. Okay, so it's not that much harder, but way more stable. Okay, so if you're using any of these methods, you know, you remember that the local error is proportional essentially for this numerical integration on one step, right? So to some derivative of the function. So here our function is changing really fast, right? So obviously, if you want to have to satisfy the tolerance for numerical error, right? Which we are trying to just. So for example, we want to compute the result with some given accuracy, right? So then what can you do? For example, you can compute with tau, right? With step tau, and then with step which is twice smaller, and see the difference between the solutions, right? So twice smaller steps supposed to give you, in most of the cases, it will give you better accuracy. So And then you can do the same for 3 times smaller step, for example. And every time you are using the smaller step as more accurate solution and looking how the difference between the solutions which you obtained in the same point, right, in the point t capital, t plus t capital, so how they differ, and use the solution which you obtained with smaller step as approximation of the accurate solution, right? So, and then you can essentially evaluate the error, because you remember that the error in this point, so what it is, it's essentially y exact at the point t plus t capital minus y numerical at the point t plus t capital, right? Magnitude. So this is the error which you need to control. It has to be less than some tolerance, right? So let's say E, less or equal, then required tolerance. The only problem is that, of course, you don't know exact solution in this point. Otherwise, you would not need to compute it numerically, right? So to do numerical computations. So this is why what you can do, you can just decrease your time step and consider solution which you obtained with smaller time step as an approximation of these, and see the difference essentially. For example, you can get y numerical with tau divided by 2 for the point t, and consider y numerical obtained with tau, and use these as approximation of the error, right? Or you can even do y numerical tau divided by, let's say, 4 these, right? And so the only problem here is the following, that essentially this is possible to do, and then you will get some value here. But it's clear that on this, let's say, last step, because here the solution is changing significantly, you would need to consider, in order to satisfy the tolerance, you would need to find the solution with smaller and smaller time step, right? So essentially, the value of this homogeneous time step will be determined completely by this last part, when your function is changing fast. Is it clear or not?
And that's not necessarily unique to this case. Like, would the error also be determined by the last step, even if we had a more like smooth, I don't want to say smooth function, but one that's less extreme at the end of the interval?
Yeah, so essentially, of course, here, this is very extreme case. So what I'm trying to say, that essentially what you do numerical integration, right? For example, let us say that you are using a left rectangle method. Then, of course, the error will be huge. If you use trapezoid method, error will be less, but still it will be significant, right? So, but idea is that where your function is changing fast, you need to use smaller time step, right? Smaller step of your numerical integration in order to get lower error. Is it clear or not?
Yeah, that's clear for me.
Okay, anybody else? Any questions? Okay, so once again, either you understand everything or you don't care. Okay, so, but it's clear that to make these small, really small steps on the part of the interval here, where your function is practically not changing, is just waste of your time. right? Waste of computations, because here on this part of the interval, so the steps which you are making will be just essentially overkill, complete overkill, because there you will satisfy your tolerance with a huge reserve. So idea could be the following, that, for example, let us compute our function up to this point using relatively rough step, right? So pretty big tau. And starting from this point, we will compute our function using the step which is pretty small. So for example, here we can make just 3 steps, and here we can make, let's say, 5 steps just on this last interval, right? So as you can see, its idea is more or less the same as what we used before. So we are using inhomogeneous grid, if you like, right, to integrate our function. So here we are using rough grid because function is practically not changing, and here we are using fine grid because here function is changing. The only problem is that usually you don't know how your function looks like, right? So of course you can do estimation of your function using some crude method and then just improve it step by step, but there is a better way of doing that. For example, let us use the following. Let us remember the methods, the order. Let us remember that we have an information about order. So I want to tell you that this is 6.5 variable step size method. Okay, so let us remember that we have an information about order of the method. If P is the order of the method. So remember that order of the method is how your error scales on the end point of the interval here, right? So global error. Global error scales with time step tau. So what can you tell me about local error? So how it will scale? If P is the order of the method, so how would the local error on one step will scale if I'm considering, yeah, how the local error will scale? With what power of tau?
The local error will scale with tau to the power of P.
No. The P is, as I said, so this is order of the method. And you remember I introduced it during the last lecture, that order of the method is how, so essentially the global error is tau to the power P.
Sorry, yeah, P plus 1.
Yes,
yeah,
yes,
plus
exactly.
1, yeah.
So okay, let us say that on the we are considering variable step size, and then locally we will have that local error on the step I will be the following: C, some constant tau to the power P plus 1, right? Okay. Then if I use E is the tolerance, desired tolerance. So then what we are trying to do, we are trying to do the following, that so essentially the error EI, the relative error YI has to be magnitude, has to be less than my desired tolerance, right? So this is nothing else but relative error. Is it clear or not? Tell me, please. So tolerance is required maximum error on the step, right? So for example, I want to compute up to the 3 digits after decimal point, right? My solution. So it means that my required tolerance has to be of the order of 10 to the minus 3, 10 to the minus 4, right? Clear or not?
That's clear.
Yeah. Okay. Okay. So this is what we require. Next. But now I can use this here, and this I can put here. So let's say that I satisfy exactly the this. So yes, or equal. So I have chosen the step in such a way that maximum step which still satisfies this less or equal, right? So then here I will use this and we'll get C tau to the power P plus 1, right? And this I will bring here. So, and I'm getting E tolerance, right? Multiplied on YI, just this. Okay. Now, what we can do, we can solve this equation for tau and C, and essentially, so what we can say that, okay, tau P plus 1 has to be E YI divided by C, right? And then from here, I will get C from here. So remember, EI is approximately C tau to the power P plus 1. So from here, C is nothing else, approximately EI divided by tau to the power P plus 1. I can substitute it here, then compute the root, and I will get that tau, the optimal tau, is nothing else but T, oh, not T, sorry, E tolerance by the value of my solution divided by this EI to the power 1 over P plus 1, right? And here is my tau on the I step, just this. So optimal optimal step can be evaluated using this formula. Of course, you could tell me that, but how do you know what is the local error? How to find? So, okay, so local error, of course, is defined as magnitude of, let's say, exact at the point t plus tau or I, but you can say I plus 1 at the next step, minus y numerical at the next step. So, of course, you don't know this. Yeah, by the way, here, usually in this estimation, usually people put something like 0.8. Let us, so requiring that, because here, you remember, we used this equality. So let us find the maximum time step which satisfies the tolerance condition, right? So gives me this equality here, right? So and of course, in order to find this, you use different, like here, for example, approximations, right? So this is why usually people put here, okay, the optimum, if you would know everything exactly, would be this, but because we use estimations, let us make a step a little bit smaller just to be on the safe side. So that there is no any way to estimate this, so you can just essentially use 0.8, for example, or 0.5, taking it twice more, but usually people use something like this. Okay, so in order to evaluate this, the problem is that you don't know exact solution. But instead of this, let us use higher order method. So, and we essentially here we are saying that let us suppose that higher order method will give us more exact solution, right? Closer to exact solution. And then the difference between higher order and lower order method. So this will be approximation of that, right? So of the error. And then we use it here. And after that, computing the optimal grid step and make the next step. I mean, so essentially we will be varying our time step on every step. So this is the previous one, and the next one is determined using this optimal step, for example. Okay, so how to do this? Let us consider so-called Runge-Kutta 2-3 method. So it's not 2/3, it's order 2, order 3 method. This will be exactly, order 3 will be this higher order method, and order 2 will be this lower order method. So this is what we will use to evaluate the error. How to do this? Okay, let me remind you what is the order 2 method essentially. The 2 method is the following, that y, okay, yeah, yi plus 1, next step is equal to i's step plus S1 plus S2. So have a look a little bit higher. So we did it. We we derived that. So multiply it on tau, right? So where S1 is, so remember, this is just trapezoid. So this is 1, this is 2. S1 is F yi ti, and S2, here is our S1, right? So evaluated in this point, and we use approximation for S2, which is nothing else but F yi plus S1 tau ti plus tau, right? So this is Euler step, right? And this is how we evaluate our function there. And then this is nothing else but trapezoid, right? So order 2 method. Okay, but we also can evaluate our function using order 3 method. And then if you have a look above, once again, you would have the following. S1 plus 4S3 midpoint here, S2 divided by 6. And this is multiplied by tau. So it's like Simpson step, right? Just in order to compute it, we need to use S3, which is half step essentially. Here. For example, this, right? Okay. So what you can see here, you can see that for this evaluation, you use S1 and S2, but for evaluation of the order 3, which you need to, in order to evaluate this, the local error, right? All you need to do, you need to compute just one extra function evaluation, right? So because you're using information from the order 2 method here, right? Is it clear or not?
I think it's clear.
Okay. Now, if you will compute EI plus 1, the error, so the evaluation will be y order 2 on I plus 1 minus y order 3 on I plus 1. And this will be, if you will just subtract from here this thing, what you will get nothing else but S1 minus 2S3 plus S2 divided by 3 multiplied on tau. So that's it. So this is the estimation, and then you use, so for tau I plus 1, the next time step, you use the following formula, 0.8 to be on the safe side, and e to the power, okay, e multiplied on yi plus 1 divided by ei plus 1 to the power 1 over p plus 1 and tau I. Okay, the question is, what power we need to use? So to be on the safe side, one could use here order 2, but you can also try to use order 3 here. So 2, or 3. And this will give you evaluation of your next time step. To be on the safe side, you can use 2. So it's more conservative evaluation of your, so you remember we use these, right? So it's a little bit more conservative evaluation. So I would use here order 2, for example. But what is also good, that you have solutions of order 2 with the method of order 2 and solution with the method of order 3. Of course, you use on every step as the final, you use solution of the order 3, not of the order 2. So a little bit more accurate, right? So essentially what you're doing, so you're using these as an estimation, right? For of the exact solution. And of course, this is what you use. Is it clear how to do this or not? So what I'm doing. So this is evaluation for the time step for the next step, right? So you are using this formula. If this was time step on the previous step, so this is what you use for the next step. Is it clear or not?
I think it's clear. So, and then for ei plus the error plus 1, you just use the approximation from above.
Yeah, so I use higher order approximation, right? So higher order solution as instead of the exact solution, right? Clear or not?
Yeah, that's clear.
Okay, so I recommend you to look at in your book. So one of the most popular methods is Runge-Kutta 4-5, which uses order 4 and order 5 methods. So if you will have a look, so it's it is our page 328. So I just don't want to rewrite this because I can make a mistake rewriting these coefficients, but if you will have a look there, so you'll find it there. And also there is page 3 or page 329, which is also Runge-Kutta 4-5, just using a little bit different methods for corresponding fourth and fifth order, because as we know, so it's not unique, right? So for example, in MATLAB, there is a command which is called ODE 4-5. So which implements exactly this method, which is on page 329. Okay, and the last thing, so let me remind you. So, for example, Runge-Kutta of the order 2. So this is what we used: yi plus 1 was yi plus f. Essentially, yeah. So it was f t I yi plus, and here we used ti plus tau yi plus 1, right? And all this multiplied on tau divided by 2. So this is trapezoid. So instead of that, we used usually yi plus 1 was yi plus f ti yi tau, right? So Euler's method. But now I can say the following. So because this is what you need to do. So this is so-called explicit approach, as I explained before. So when you know explicitly how to compute this using just yi, right? But what you can do, you can say that, okay, I don't want to do this like that, but I will consider this as nonlinear equation for yi plus 1, which I can solve using, for example, fixed point iterations, right? So s plus 1, s. So you can use, for example, here your previous approximation and hope to get better. So of course, fixed point iterations, you need to learn whether they converge or not, so it's not that easy. But this is so-called implicit method. So essentially, when you're trying just to solve this nonlinear equation for yi plus 1 using Newton, fixed point, whatever you like, or even bisection. So this is another approach, but we are not doing this. So I ask you to do this only for this extra credit homework. Okay, so this is where I will stop.